Good afternoon, everybody. Welcome to the session about open source software in space operations. We will be having two speakers with us today. First up is Tom Mladenov. Tom obtained an MSc in Electronics and ICT Engineering from KU Leuven, Belgium. He worked on a quantum magnetometer that recently returned from the ISS with SpaceX CRS-25 Dragon capsule. Tom was the lead payload operations engineer for the European Space Agency's OPS-SAT mission, Europe's first HWSW innovation platform in LEO. He currently works as satellite operator SES based in Luxembourg. Mr. Mladenov, you can go ahead.
Okay, thank you, Rima. So welcome everyone. Good morning, good evening from wherever you're joining. Josh and I were really excited today to give this session at the Space Education Strategic Applications Conference 2022, and we'll be talking about open source software in space operations. The purpose of this talk is to share the opportunities, challenges, and lessons learned from pioneering open source software usage in an operational space agency mission, which is OPSAT. Josh and I were both part of the flight control team at the European Space Agency of OPSAT, and we'll use various examples of this mission to elaborate on the open source software usage that we had in this mission. As well, we will propose ways forward to drive innovation in this domain and the best practices on adopting and deploying open source software for space and ground segments. We've already had the introduction, so I will not repeat it. I will do a first part of the presentation. We'll switch to Georges, and then we'll finish with the last part. So for the program for this presentation, first we'll talk about OPSAT itself. What is OPSAT? And then we've got three pillars that make up this talk. We'll be discussing open access in this scope, the community outreach and support, and looking to the future. So let's first talk about OPSAT. So OPSAT is a 3-unit CubeSat, which you can see on the right there. So it's you can see there the solar array wings in the clean room, and it's the first CubeSat that's directly owned and operated by the European Space Agency. And it's currently orbiting in low Earth orbit at a orbital altitude of 515 kilometers. And was launched in December of 2019. And the goal of this mission is to test out new operational concepts, which help us to break the has not flown, will not fly barrier, which is present in space operations. And it's devised as a way for industry and academia, universities, startups, large corporations, to test out new software concepts on a satellite. And the advantage is that as if you're an interested party, you don't have to launch your own satellite and test it. You can use this platform that ESA offers for free. So to facilitate easy and free access to a satellite to test new risky operational concepts. And I think also in the meantime, Georges will provision some of the URLs so that you can have a look at those sources while we continue with the presentation. So to continue on OPSAT, the satellite launched in 2019 is based around a Linux payload computer. And a bit more in detail, it's an 800 megahertz ARM Cortex A9. And we offer a range of interesting payloads on the satellite, such as a field programmable gate array, which allows interested parties to experiment with IP cores, etc., as well as a software-defined radio, laser receiver, star tracker, and X-band radio. So you can see an image on the right there with the location of those various payloads and sensors. As I said before, we launched 18th of December 2019 in a 515-kilometer orbit. So that's OPSAT. And so far, we've realized a range of interesting experiments ourselves internally at the European Space Agency, but also for all experimenters, so for all external university startups. And just to give you a couple of examples on what we've realized so far on OPSAT. For example, innovative telemetry and payload data compression, convolutional neural networks on FPGA, for image classification, but also cloud mask detection, for example. We've tested the in-orbit reprogrammable software-defined radio for tracking emergency beacons, but it could also be reprogrammed to track wildlife beacons, or Internet of Things sensors. So really the focus there was on reprogrammable. We've also participated in delay tolerant networking experiments with D3TN, which was also performing interoperability tests with the new NASA bundle protocol. And also to continue, we've deployed on-orbit machine learning for anomaly inference from telemetry on board the satellite itself, as well as image type inference and cloud mask generation. So a couple of partners we've worked with there. And again, all these experiments were carried out for free on OPSAT. And yeah, to just briefly show what those experiments look like. So these are all data products downloaded from the satellite. So we've got, for example, in orbit RF measurements, so essentially a spectrum analyzer in space. We've done wildfire detection from space, RF analysis, like I said. Here on the bottom right, I think I have a laser pointer somewhere. Anyway, it will pop up on the bottom right, for example, cloud mask detection, RFI mapping, and also orbit determination. So just to give you a brief example on what those experiments typically look like. Let's talk about the first pillar of the presentation. So open access. OPSAT uses what's called the NMF, which is the Nanosat MO framework, which is linked here below, but we will provision the link separately. And it's a software framework for small satellites that we have developed internally at ESA a couple of years before launch, and it looks at the problem of running software in space. It looks at it a little bit differently, and it generalizes software as apps. So we could run apps in space, which are singular software processes that can be started and stopped with a particular purpose. So one typical experiment would be an app which would be started and stopped in a particular part of the orbit of the spacecraft, or left running for that matter. And the focus here is really on payload abstraction, because whether it's on a small satellite or on a very big satellite from another space agency, if they both have a camera, then there are a lot of parameters which are common, like exposures, gains, etc. So all these parameters are, as part of the NMF, abstracted as via the payload interfaces, which we'll discuss a bit further in the presentation. And again, here, so simple interfaces, transparency, and it looks at the problem in a new way of sort of compartmentalizing applications running in low Earth orbit. So for like we call it Space Platform as a Service, or SPaaS. And the goal here is to also move towards multi-purpose shared missions with a single satellite, because what we've already demonstrated on OPSAT with having a range of interesting payloads, we can accommodate a breadth of experiments, and therefore each of those experiments is also on its own a mission, whether if it's detecting wildfires, doing global radio frequency mapping. So in a sense, with only one satellite, with the various payloads, you can perform various missions. So that's also paving the way for multi-purpose missions. And as part of OPSAT, it now has over 2 years of flight heritage. Bit more in detail about the Nanosat MO framework. So on the bottom right, you can see a block diagram where the yellow parts are actually from the satellite, and the NMF is highlighted here in red. So the various payloads, which you can see on the far right, the software-defined radio, cameras, optical receiver, they all interface with the payload drivers, and the NMF communicates with those payload drivers via an API. So the way of interacting with those payloads is sort of is abstracted away by the API, which is then used by the experimenters to realize various functionalities within their experiments. So it might consist of a combination of usage of the payloads. It depends from experiment to experiment. And the applications are also free to include any required libraries for image processing, RF signal processing, etc. On the ground segment, so the bottom two blocks here in green and blue feature the ground components. And what's important here is that the interface that we expose to the experimenters there are a number of different interfaces. So one of the most interesting one is a web browser. So via a web browser, the experimenters can interact with their application running on board. So they can send various commands when the satellite is in contact with ESOC, and they can receive their telemetry, download data products, images, etc. So this is essentially the ConOps or concept of operations for OPSAT. Now, takeaway that from the open access is that by having a shared platform in low Earth orbit where you can run applications in a compartmentalized manner, it essentially opens up a whole range of opportunities, which we've seen during the course of the mission. So essentially, it's an open source framework for testing new applications in space. But more importantly, missions like OPSAT, they lower the threshold to innovate in space. Because if you're a startup and you want to demonstrate and test a new operational concept for image processing or RF signal analysis, you don't have to launch your own satellite to get the flight heritage. You can try it out on platforms like OPSAT and validate your concept that way and improve it before you move to a dedicated satellite. Okay, moving on to community outreach and support. Again, we'll use a couple examples from the OPSAT mission, which also revolve around which were powered by open source software, and we'll show how these helped the flight control team, how these helped us in the mission essentially. And we'll begin with amateur radio. OPSAT, like I mentioned at the beginning, is the first ESA-owned satellite, but more importantly, it uses the amateur radio spectrum for one of the radio links. And this essentially means there are a couple of obligations. So there is a public call sign that we request, but because we're using amateur radio spectrum, which is a public frequency allocation, we have to publish the frequency modulation and data framing specifications. So on GitHub, there is all the information on this about OPSAT. And we even went a step further to really leverage the open source software, which is GNU Radio. For those of you that don't know GNU Radio, it's a free signal processing toolkit or library, let's say, which can split a complex signal processing task into various simple tasks and build signal processing flowcharts by means of individual blocks. So we wrote an application which is based on GNU Radio, which is open source, which allowed the community to use commercially off-the-shelf hardware, such as a typical software-defined radio, which allows them to demodulate and decode the beacon that is transmitted from the satellite when it's deployed. So this is the application here. You can see on the left a tracking application, gPredict, and on the right is the application used by a radio amateur to receive beacons from the satellite. And again, this is linked in the WOVA stream. And to continue on for also focusing on the theme of space education, we've had a lot of contact and outreach with various university research groups. So students which were very actively engaged in tracking OPSAT. So there was a couple of weeks leading up to the launch campaign, we've had a lot of interaction with those teams. So you can see here on the left, a student team from Germany in Aachen, preparing their ground segment, let's say, with the software that we delivered, that we built around GNU Radio. So they were getting ready to track. We've also had a group of radio astronomers in the Netherlands, which had access to a radio telescope, join in on the signal hunt after the spacecraft separates. So that was really interesting to see. And yeah, on the right, you can see actually the signal reception, the first beacon that was received by one of the radio amateurs in the far north in Europe. So that was certainly already good to see, because before we made contact with our own ground stations from the ESA network, we already had an external verification that the satellite was transmitting and the parameters in the beacon downlink were nominal. So again, one of the advantages of already upfront publishing these applications and this information, because it was very quickly integrated into also the amateur radio community. So that was certainly very, very helpful for the mission. And not only the application that we wrote, there's also what's called the SatNOX project, which stands for Satellite Network Operated Ground Stations. And it's a community sourced network of receiving antennas. So we also coordinated with them. And very quickly, an entry was created in their system to track OPSAT. And this essentially meant that hundreds of antennas and ground stations around the world were already pre-configured for receiving OPSAT. And this, of course, this helped enormously. Because when the spacecraft separated, it was not yet in view of one of the ESA ground stations, but it was in view of some of the SatNOX provisioned ground stations, so the community sourced ones. And again, the signal decoding application that these ground stations use are also based on GNU Radio. Here is an example of the various SatNOX ground stations. I think this is a rather old shot, so it there should be plenty more by now. But to give you an idea of the geographical distribution. And to top it off, we also in the week leading up to launch, we spread this news to the radio amateur community and to inform them on the launch window, launch timing, when the spacecraft would separate, and to sort of challenge them to be the first person to receive the telemetry downlink and forward those signal reports to ESA, so we could have upfront verification. So this was very successful, and this news spread very quickly. So this was definitely great to see. To see this global hunt, let's say. This is also an interesting plot showing the coverages. So each dot represents the Earth location, so the ground track position where the satellite is over when a beacon is received from space. And in red is the ESA ground station coverage, so which was done with 2 UHF ground stations. And in blue are the community sourced coverages. So you can see a lot of coverage in the US, definitely on the eastern seaboard, but also on the west side, where actually the first signal report after separation was received. So definitely a good distribution there in the community. These are the various stations actually that received various frames. So the distribution, so some stations were continuously tracking OPSAT, other ones were tracking other satellites. But again, it was good to see the community prioritizing OPSAT and taking various passes, especially early after the launch, let's say. We can see here, yeah, on the vertical axis, the number of packets that each station has received. Okay, and now I will hand it over to Josh, who will continue in this pillar of the talk, but will focus on crowdsourcing AI innovation on OPSAT.
All right, thank you very much, Tom. Just a quick intro for me. I am also formerly part of the flight control team at OPSAT in ESA, and I did a lot of the work pertaining to first experiments of application of machine learning and AI on board a flying mission, in this case, OPSAT. So I'll give you some storytelling on how this involved the crowd, and a lot of the technologies we used are open source technologies that enabled engaging the crowd and engaging the expertise in that open source community. So yes, Tom, we can go to the next slide now. This whole idea of crowdsourcing for innovation in general, not just for AI, you've seen a bit of a preview of this with Tom, with the Radio Amateur group, where we're relying on the crowd to help us problem solve and help us engineering problems. And this is only possible if you make a platform that's openly accessible, and it has even more chances of success and engagement if it involves a community that already exists. And a large community that's super passionate is the open source community. So what's the idea behind crowdsourcing AI innovation? There's this idea that we want to do some right tail sampling to unearth distance expertise. So flight control members for the OPSAT mission, and I'm guessing many missions, we tend to have a bit of a tunnel vision based on heritage on how to operate spacecrafts. A lot of it based on our background with working with embedded systems and having this electrical engineering background, this software engineering background, which is really close to the machine. And then suddenly we have more powerful computers, and then we can run these new technologies, more modern applications, but we're stuck with our tunnel vision here. So what we need is outside perspective to take advantage of this new environment in a way that's meant to be used in a way that's enabling. So what we find with crowdsourcing innovation is that there's a phenomenon where the best open solution, which is here in this pink area, the best open solution from the crowd tends to be greater than the average solution from the expert, and the expert curve is the orange curve here. So you see the average best solution for the expert distribution peaks, but when we source from a crowd and when we source from interdisciplinary and when we source from fresh perspective, then the best solutions is greater from the crowd. It might be, one solution out of 1,000, out of 10,000, but still the best could be from the crowd. In this way, novel solutions, they can be contributed from outsiders because they have a problem-solving mindset that's from a different discipline and adds fresh perspective that we internal experts are probably lacking due to our tunnel vision. This is a whole motivation behind crowdsourcing AI innovations. And how have we applied this on OPSAT? Let's look at the next slide. This was the very first application of onboard inference that we know of in the public domain, at least, and it was onboard OPSAT, where we were trying to solve a problem. Say, okay, we're downlinking images that are not great because we're still working on the commissioning the spacecraft, and sometimes when we're taking a picture, it's pointing in a non-deterministic way, so we're getting bad images. And we're wasting all of this bandwidth downloading the bad images when we could be using it, downloading or downlinking valuable science data instead. So what the flight control team said is like, okay, this sounds like, machine learning image classification one-on-one. We have these open source environments, Linux, and a payload computer that can run Linux, and we can run open source machine learning technologies on board, specifically one called TensorFlow. So we trained a model that's able to distinguish between these three images. But us in the flight control team, none of us are AI ML experts, or maybe we weren't so much involved back then. And this was the extent of our expertise. We can train a model to distinguish between these three types of flagrantly different images, but don't ask us to do anything more sophisticated to this because we're flight controller people, we're not machine learning or AI people. But the way we built this, it's called the SmartCam. The way we built it was a pipeline that could be fed models that were contributed by the community. So if we go to the next slide, maybe I developed a model that can classify that can figure out if an image is edge, bad, and earth, because that's the level of expertise I can obtain in like a 2 weeks notice of research. But now that the framework is in place with open source technologies, we attract community members from that technology, and then they can suddenly plug into a system. So we're inheriting the expertise to go more finer grained in our image classification. So maybe Janet did a first version of the model, and then we can subclassify the output from Brad's expertise in cloud detection, for instance. Next slide. But what does this mean in terms of ecosystem of technology that we're using, open source technology? So none of the technologies we're using are new in terrestrial applications. They've matured over many years for mobile edge devices. This technology, it exists for these phones, right? That's why they were developed, and that's why they are resource aware. But now we have the type of processing power on the spacecraft that we can use those terrestrial applications and technologies and run them on board. So what happens here? In the case of AI, we have all these open source technologies for data development and training and evaluation. So the middle left part of this slide. But instead of just using those tools to deploy on classic terrestrial applications on the right, next slide, we can use the exact same tools, but just deploy our solutions on OPSAT. And that's exactly what we've been doing. We say, hey, we deployed this technology on the spacecraft. It's well known on the terrestrial world, on the open source world for mobile application development, but now you can use it to write and deploy software on a spacecraft. Next slide. And I'll give you an example of this. For instance, we partnered with MIT Star Lab on cloud detection. But how did this start? So if you look at the left side, this is a nice picture of Vladimir, one of our flight control team members, taking a picture with the engineering model of the satellite in the lab. So we have a replica of the satellite in the lab where we run tests. So he's posing here in front of the camera. And I wanted to experiment with an algorithm to segment the image into different groups based on similarity. In this case, it's kind of reliant on the color coding, RGB color coding. So I said, okay, segment this image in 4 groups and tell me what kind of 4 groups you come up with. And then this was just a playful thing we did at the lab to experiment with this algorithm. And you can see the nature of how playful the idea was by just using a selfie taken from the engineering model of the spacecraft. And then some of us got more involved because this algorithm that we used is quite a popular algorithm in the AI and machine learning community. It's called K-means. And then we started realizing, hey, wait a minute, we can start using this for cloud detection. So here you see 3 different scenarios in the middle: cumulus clouds, stratus clouds, and then clear skies. And we're able to do some cloud detection and classification from this algorithm that we just downloaded online in GitHub. It was open source. And that was still kind of playing around, yeah, cloud detection, but we're not operationally using it. But we wrote a paper about it and we published and said, this guy has great potential. We haven't explored or optimized it. We just know that we can run these types of algorithms now on a spacecraft. And that caught the attention of some folks over at MIT who are developing a cloud detection and segmentation algorithm for their own CubeSat called Beaver-Cube 2 that's soon to be launched. And they said, oh, we want to use this, but also we want to run our own algorithms on your spacecraft in order to benchmark what we're working on and optimize it for our launch. So what has happened is that OPSAT has essentially become a platform of a service, as we're calling space, to de-risk future missions. So you have multiple algorithms here on the right side developed by MIT, one based on luminosity, C, one based on random forest, E, and F, it's a neural network algorithm called UNet. And number D, K-means, that's the one we developed with the on the left side here that we used. So they developed their own thing. They ran it on the spacecraft and they benchmarked against the same image. The spacecraft took an image, we ran the 4 algorithms, and this is the result of cloud detection for all 4 of them. And the reason why this came to be was, again, use of open source technologies and outreach from the community of machine learning. They were very involved in this type of research of using open source technologies for machine learning and cloud segmentation. And what happened in the end is that they've validated their algorithm, they've published their algorithm, they're going to launch it in Beaver-Cube 2, And during the process, we've inherited those algorithms for the spacecraft itself. So when we went from a playful concept of just going, I wonder if this can work on the spacecraft. Oh, great, it works. What's next? I don't know. We ended up, through contribution from the folks over at MIT and pushing towards availability of open source technologies, on an operational value of those algorithms that just started with playing around with open source. Let's move on to the next slide. We're taking this a step further. The OPSAT team is taking this a step further in collaboration with PhilLab, the Earth Observation Laboratory in Friscali from ESA, where now they're creating a competition from their platform called the Kelvins platform. And this is a platform developed by the Advanced Concept team in ESTEC, again, ESA. So what they're saying now is they're saying, okay, we have these images. You only have 10 images, right? And you need to figure out how to train a model that can distinguish between those images and tells us what it is. Because the reality of the resource constraint in space is that for a given experimentation time, we can probably just take 10 images, and that's what you have to train your model and classify your image for yourself. So the Advanced Concept team with the Kelvins Challenge created this environment that replicates the spacecraft, and anyone can join. It's a 2-month-long competition. It started in July, it's ending in the end of October, where they train models, they use whatever technology they need to use, as long as it runs with the framework we've installed in space on the spacecraft, the TensorFlow framework. And they test and point against each other, and there's a leaderboard. And the winner of that competition will get to run their model and collaborate with the flight control team to get their experiment and their model plugged into our system in an open, innovative way. So it's really cool. Submissions are ranked. There's a competitive aspect to it. Teams can be formed, and there's a lot of collaborative effort, and people chat on the forums. It's really cool to see progress and optimization of those models progress over time due to the challenge nature of this. It's really cool. Check it out. Next slide. So what are the takeaways here? We presented 2 really case studies, one for the GNU Radio from Tom, and one on AI using open source technologies to run on board of the spacecraft. We found out that we could really rely on a wider and broader community to solve critical operational problems. I said it on the chat, the SatNox community pretty much saved the mission. When nobody in the flight control team knew where the spacecraft was, we got a response from the SatNox community that really helped us locate it and work from there. Again, great community effort and great communication effort to get the community ready for this launch. The biggest takeaway of the work with the AI frameworks we used is that because we used popular frameworks that are used in different disciplinaries and industries, we really got the talent and the different perspective from others. And we really inherited a way of writing software that is typical in modern private sector agile development, but atypical in the space sector, where we're building software fast, prototyping, launching new versions of the experiment every week or every other week, and doing quick iterations in rapid prototyping. It was really cool to see that speed of frequency of iterative development on these experiments. Tom, I don't know if you want to add something in particular before we move on to the next section.
Thanks a lot, Josh. No, you've actually covered all the points from that section. So I propose that I'll finish. So now, having taken note of all that, what's up for the future? Now let's have a look. So we definitely already see. We should have probably also mentioned. I've also been the past week at the IAC, the International Astronautical Congress in Paris. And there's definitely the upcoming market interest in space, satellite platform as a service, and DevOps for space. So essentially, the multi-purpose mission concept that we talked about with the payload sharing, the interfacing to payloads, with applications running on board in a compartmentalized fashion. And all these will allow the lowering of thresholds for space innovation. And also enable sustainable space operations. Because when we're able to deploy multi-purpose missions, we can accomplish the same tasks with only one spacecraft. Therefore, also do not contribute to the growing space debris problem. So another aspect to take into account here. And also, finally, the further adoption of DevOps principles, like George said, like George mentioned, with the overview of all the excuse me, all the terrestrial software that's already well proven, well tested, well integrated, to have those flow up rather, into various aspects of space missions. So both the ground segment, like we've shown with GNU Radio, with signal processing, signal decoding, but also on the space segment, onboard the satellite itself. So takeaways from this, that to summarize, we already see more platforms like OPSAT being readied for launch, offering satellite platform as a service, and as a combined effort to further adopt the ground-proven software workflows, but also the software itself, into space operations. And a major contributor in that part is the open source community. So, summary of all the takeaways. We've talked about open access. We've presented OPSAT in the beginning of the mission, beginning of the presentation, which is a readily accessible platform and is was conceived to allow lowering the threshold to innovate in space by allowing universities, academia, startups, large corporations to deploy applications on board OPSAT and gain flight heritage that way before moving on to dedicated satellites. As part of community outreach and support, we've seen that allowing and also reaching out to the community, so making the first step, can spark various discussions and exchanges that in the end have, like Josh said, have benefited the mission when there were communication problems with the satellite, for example. So sums it up quite nicely: by the community, for the community. And then finally, when we look to the future and see what's happening right now in the new space industry, we already see platforms like OPSAT being ready for launch, which will drive the further adoption of terrestrial software into space operations, and also do this in a sustainable manner. Like we mentioned, with multi-purpose missions, payload sharing, ride sharing, etc. So we're well on time, because this will allow us to also open it up for the questions and start interesting discussions. Like Josh said, we also have a range of other publications that cover each of the examples we've shown in great technical depth, mostly in conferences and various journals. So they're here. We will also post a couple more links later on via Wova, so that you can check those out if you're interested. Finally, I would also show you the contact information if you have more questions, which there are some questions in the end of the session which cannot be answered, then feel free to reach out to us, and we would be more than happy to engage in the discussion. So with that, I think we can open it up for the Q&A.
We will wait a few minutes just to have people come up with any questions. And if not, then we will conclude there, but we'll wait a few minutes.
Okay, perfect. So yeah, if there's any questions from the audience, please feel free. Both Josh and I are monitoring the channel, so feel free to shoot. If there are no questions in the meantime, I think we can already discuss the one that was asked in advance. So the question is, will open source software be vulnerable to detrimental entities, hackers, unfriendly nations? So yeah, very, very good question. Josh, you maybe want to take this one?
Yeah, I think the greatest example I can give is when technology is open source and accessible to all, there is an additional incentive to focus on security with that technology. Because when something is openly available, you develop a more robust system. And I think the perfect example for this is in the world of cryptographic algorithm. One of the golden rules of developing a cryptographic algorithm is that the algorithm itself needs to be open and visible. Like you have to be able to see the implementation of the algorithm. And why do we want that? It's because we don't want people to put in hard-coded proprietary things that could be hacked and uncovered and then compromise the algorithm. We want the cryptography itself to be algorithm independent in terms of its security. So I think if we want to be concerned about open source technology, it's not so much about security, because that is very robust in that aspect, but on how do we create an environment to support ongoing work and support people who use that open source technology. TensorFlow is a great example. It's a tool you can confidently use that will always have updates and security updates. But what about for smaller tools that have, or smaller frameworks that have great potential but little support?
Okay, thank you, Josh. Any other questions that have come up in the meantime from anyone in the audience? Then feel free to let us know.
So someone asked if there was a list of programs somewhere.
Yeah, I think question by Michael, right? Yes.
Exactly. So unless, Michael, please correct if I misinterpreted this, but I'm assuming you're meaning the experiments that are running on board the spacecraft. We don't have a comprehensive list of everything that's been developed for the spacecraft, but I would encourage you to navigate through either Tom or myself, my profile on ResearchGate or on Google Scholar. And it's a good start to at least appreciate the capabilities of the spacecraft. I would also encourage you to join the community platform. Tom, if you could maybe put the link on the chat, where there are references there and discussions and ability to contact the flight control team to get a better idea of what the state is of the spacecraft in terms of experiments and what's been done.
Okay. Yeah, I've just posted the link to the community portal that Josh mentioned, which is the central place where all experimenters have individual accounts and use it to exchange with the flight control team. So that's available for you in Wova. So, any other questions?
I'd like to add to that, like what's happened quite often when experimenters join and are interested in developing an experiment is that they come up with an idea and then they get this continuous feedback from the flight control team. It's like, oh yeah, these experimenters did something similar, or these other guys did that. You could collaborate or build on top of this. So it's really cool to see how people are not just isolated with their own experiments, they're building on top of each other's experiences with OPSAT. I see there's a question in the Zoom Q&A. feature?
I will wait. I have to.
I'll read it to you. It's from
Okay.
Bridget Varela.
Mhm.
Sorry if I mispronounced the name. Is there only one OPSAT? And if so, is there a plan to have more? I can provide a bit of an answer on this. There are early designs being thrown for OPSAT 2, much bigger comparative to OPSAT 1 in terms of the satellite size and capability. I've also heard it through the grapevine that there is talks about a in between OPSAT 1 and OPSAT 2, something like OPSAT Lite, but still in the very early ideation phase. So definitely a success story to validate a next mission that's currently being discussed. No idea on timeline though. So Tom, I have a question for you.
Yes.
Since you're fresh from the IAC
Mhm.
conference, what is your assessment of the way forward you've concluded with and what you've observed at the IAC?
I mean, it's yeah, it was part of what you mentioned, right? That there's definitely a big movement in the also I would say the modular way in which you can now buy commercially off the shelf payload. So it's SDR transceivers and also system on chip. So it's becoming from hardware, from what I've seen from the hardware side, it's all becoming very modular and very pluggable, and it's becoming easier to, let's say, tailor and customize your own platform. Because when we procured the units for OPSAT at the time, so with launch in 2019, the hardware procurement started 2017. There were barely off-the-shelf, easily interfaceable units available for the configuration that we wanted for OPSAT. And this, fast forward 5 years, is now completely different. Now the difficulty is making a choice of which vendor to use. So definitely, it's become much easier to get the configuration. And then also there's there, like I said, there were various new onboard processors, so even more powerful than OPSAT. Because at the time when we launched OPSAT, like we mentioned, the 800 megahertz dual core ARM A9 Cortex processor. At the time, this was the ESA spacecraft was the ESA spacecraft was the most powerful computer in orbit. But nowadays, with what's available and what already has been launched in the past year or so, are now baselining those processors with similar or even better performance characteristics. So this again, we see in the various domains for both the payloads as well as the onboard computers themselves, which control the actual satellites. So it's definitely good to see the nano satellite market going into this direction, focusing on those aspects. So yeah, thank you, Josh, for that. Okay, I think there's also in the meantime a new question from Maurice. I can read it out. So From Maurice, we are the High Alert Institute, and we have a space, healthcare, and AI medicine policy working group that is developing frameworks for healthcare regulation, practice, ethics, and community standards of care in space and future habitations, including interglobal decentralized health AI outcomes database that will be open source. We are interested in discussing synergies for the AI and open sourcing. Please email. Okay, we will. I think it's not a question. It's an invitation for further discussion. So we will certainly take note of that, Josh, and then reach out to Maurice, because it certainly, like you mentioned, sounds like there are synergies.
Yeah, and the interdisciplinary aspect of this is really extremely valuable. When I was trying to figure out to do basic image classification with AI on board a spacecraft, like the very first division I showed in the slide, bad, Earth, edge, I started with YouTube videos. It's like, okay, how does this work? How do I train a model? How do I use open source technologies? What can run on the spacecraft based on my assessments from YouTube videos? And I stumbled on this channel of this gentleman who had really great tutorials. And turns out that he works at a company for microscopy, and he's doing image processing for microscopy and medical related health checks. And I had a meeting with him, and then he helped me so much to get started with image processing from his knowledge at microscopy that I could transfer over into my knowledge in space sector and apply it to image processing from images taken from low Earth orbit. So there's definitely value in this both ways. So we'd be interested to talk.
Perfect. Okay, we still got a little bit more time until there is the closing keynote, which is at 10 past. So if there's any other questions, remarks, or invitations like this one, then please let us know. And then we'll discuss.
I think we can defer to our moderator on whether or not we want to stick around some more or wrap up.
Yes, if there are no other questions, then we can definitely conclude here. Thank you both speakers for speaking with us today, and that will wrap things up. Thank you so much once again. Have a great rest of your day.
Thank you, everyone.
Okay, thanks everyone for joining, and enjoy the closing remarks. Bye.